Hi guys, today we are going to have our first video in a long time, but today we're going to talk about two things if we have time. The first thing we're going to talk about are Kirchoff's laws or rules for circuits. There are two of them. And then the other thing we're going to discuss are RC circuits if we have time in this video. If not, they will be in the second video. So let's go over Kirchoff's laws for circuits. And we actually have already been using them. You guys just haven't been aware that we have. But he has two, actually I think they're really called rules. He has two different rules for circuitry. And the first one tells us that the current traveling into a junction has to equal the current that comes out of that junction. So we do this whenever into a junction equals current out. So we follow this rule whenever we are doing parallel circuits, and the current will flow into a junction here, and then maybe it'll split between two different branches. So this law says that this current has to equal these two added together. The second law says that around any closed loop, the sum of the potential of the change in potential must equal 0. So we've been doing this whenever we do a series circuit. The idea that the voltage that's coming out of the battery gets split between all of the resistors in series, but that when we add up all of that voltage across those resistors, it should equal the voltage that's coming from the battery. So this first one is sometimes called the junction rule. And this one, okay, the sum of the change in the potential is 0. So this is sometimes called the junction rule, and this is sometimes called the loop rule. Junction rule, a way to think of it, would be conservation of charge. You can't all of a sudden create more current when the current has already been established unless you took out a resistor or put more batteries in. And then this one you can think of as being conservation of energy, right? The energy that goes into the circuit has to be the energy that's going to come out of it across the different resistors. So we're going to do Kirchoff's rules for a couple of different circuits. They really come in handy whenever you guys are looking at a circuit that can't be solved using our traditional methods, meaning using Ohm's law and reducing it down to one resistor. There are some circuits that doesn't work for. So we're going to do one now. I can show you when using Kirchoff's comes in handy. An example of when it may is when you have two batteries, or even more than two. You could have 3 or 4. So let's make a little series circuit here. Let's put another resistor there. And then let's put one down here. Okay, so let's say this is 12 volts. And let's say that this little resistor is the internal resistance of this battery here. So I'm just going to drop this around. And here. Alright, so let's say that's 12 volts. Let's say this is a 9-volt battery. And let's say that these resistances here are 1 ohm each for the internal. And let's say this is 4 and this is 5. Okay, so I'm gonna show you guys how to use loop rule first, and then I'll give you guys an example of how to use the junction. We don't have any junctions in this circuit that I drew because it's just one loop. The current doesn't split out at any point. So what we do whenever we use Kirchoff's loop rule is you need to pick a point on the circuit. It doesn't matter where you start. I like to start near one of the batteries, but it doesn't really matter in the whole scheme of things because we're going to go around the loop and calculate the voltage drop or the voltage gain across each one of these resistors. And the total of all of that put together should be 0. So I'm going to start right here, and I'm just going to label this position A, and I'm going to do my current in this picture in red. So what I'm going to do is I'm going to assume that the current will be flowing clockwise. That might be wrong, and that's okay. If it's wrong, you'll get the right answer. It'll just be the opposite sign. So we'll start here, and I'll show you guys what that means in a second. And I'm just going to pretend like I'm the current, and I'm traveling through my circuit. So I'm here, and I'm going to go across the battery. I'm going across the battery from the negative end to the positive end. So that means that I'm going to gain some potential. So how much potential do I gain? Well, I'm going to gain 12 volts. All right. Remember, we're adding up all of these gains or losses, and they should all equal to 0 when you add them all up together. So keep going, keep going, keep going. And now I hit a resistor. Well, what would be my voltage drop across that resistor? Well, that would equal IR on this resistor. So we don't know what our current is, but that's the point, right? That's going to be the point of this question, is to use the loop rule to find our current. So we're just going to label that I, and we're going to multiply that by 1 for the resistance. Keep on going. I hit another resistor. Oh, sorry, that's not an addition. That's a drop. So anytime you have a voltage drop, of course, you're going to subtract it. Anytime you have a voltage gain, it will be positive. So go across the 4 ohm resistor. That's another voltage drop. So that's 4 times the current. Keep going. Another voltage drop. I times 1. And now I'm going to go across another battery. But this battery, when I travel this direction, now I'm going from the positive end to the negative end. So I'm losing potential. So I'm going to lose 9 volts of potential. Keep going, keep going, keep going. And go across that 5 ohm resistor. And then I'm right back where I started. So the loop rule takes you around a loop with you figuring out whether you're gaining or losing potential at every spot. So what Kirchoff's law tells us is that this should equal 0. So the change in potential should be 0. So 0 equals 12 minus I minus 4I minus I minus 9, I'm running out of room, minus 5I. Alright, so let's go ahead and simplify this as much as we can. So 12 minus 9 is 3. And then that's 4, 9, 10, 11. So we bring our 3 over to the other side. And we get a total current in this circuit of 3/11 amps. So what I meant earlier when I said if we picked the wrong direction, if we went around the other way, well, nothing would really change in this problem except for our signs on our batteries, right? Because if I went this way, I would be gaining 9 volts and losing 12. So what you would end up with, let me just go ahead and put this here. So what you would end up with is the same numerical answer. It would just end up being negative. And then that would be a pretty good hint to yourself that you needed to switch the direction of your current. Yes? Is that yours? Okay. Alright, so that is essentially how you use the loop rule. You're just going to go around the circuit and you will add up or subtract the voltage drops across each piece in the circuit. So let's go to junction rule now. It doesn't look like we're going to have time to do RC circuits in this video, so we'll save them for later. So let's do junction rule. What junction rule helps us do is find the current in a circuit if there are multiple loops and multiple batteries. So we're going to draw a circuit for this. Here's one pretty easy loop. And here's another easy loop. Alright, here we go. Let's do 5 here. Let's do 5 here. Okay, so this again is another example of a circuit that you can't really reduce down into one single resistor. You have multiple batteries, you have multiple loops, you have different things happening and different currents in different spots. So it doesn't really work. We have to use Kirchoff's to do this. So the first thing we're going to do is kind of the same thing I did with the junction rule, in that I'm going to pick a spot. So I'm going to choose here, right past my battery. And I'm going to draw what I think the current is doing. It's okay if I'm not right. Again, your answers will just have their sign reversed. So I think I'm going to say that the current's going to come around this way, and then it's going to hit this junction here, and it will split between these two. I'm going to call this current I, and I'm going to call this current I1. And this current I2. Okay, and so what the junction rule tells us is that I equals I1 plus I2. Alright, so I've done that. I've described what my current is doing. Now I have to use my loop rule to kind of piece this stuff together. Now I have 2 loops. Actually, in this question I have 3 loops. I have this loop, I have this one, and then I have the big outer one. It doesn't really matter which loop you choose because it will all be the same anyways, but for this one I'm going to choose the big outer loop. And I will do Kirchoff's loop rule for this big outside loop here. So let's put little steps. Step 1, determine current flow. And after you've kind of hypothesized what the current will do, you need to write a formula that describes it, like I did here. So the second thing is to apply the loop rule to a loop in the circuit. It does, like I said, it's not really going to matter too much, but I'm going to do the outside loop. So that means I'm going to, I'll start right here so I get a little potential gain first. So again, I'm going to follow my current around. So here to here, that would be, this is all going to equal 0. So from there to there, potential gain of 9. And remember, I'm just going around the outside loop. Go through here. Now I'm going to have another potential drop, but that potential drop, remember, is going to be equal to 3 times the current that's flowing through it. The current that's flowing through 3 is I2. Alright, keep going, keep going, keep going. I have a drop in potential of 5. Keep going on the outside, and now I have another potential drop, but you have to be careful about what current is flowing through to the 2 ohm resistor. So I1 travels through here, hits this junction. I2 travels through here, hits this junction. They recombine to make my original current I. So that means that 2 I is flowing through, or that's the drop across that resistor. And then I come back to my starting point. So that's my equation for the outer loop. So now what I can start to kind of do is see that I have two formulas for my circuit, this one and this one. And I can combine them together to put them in terms of I1 and I2. So I'm going to go ahead and do that where I can. 9 minus 3I2 minus 5 minus, now I is I1 plus I2. Right? So I can go ahead and combine 9 and 5 to, I'm just going to simplify this a little bit for us. 2I1 minus 2I2. So again, negative 3 and negative 2, that's negative 5. Alright, so there's my expression for the first outer loop. So I have a problem though because I still have two unknowns. You actually have three unknowns. You have the total I current, you have I1 and I2. So it's kind of a big hint that if you have three unknowns, you're going to need to use three formulas. So I've done the loop rule on the outer loop. It got me an expression for my current, but I haven't really can't really use that to do anything with it. So now I'm going to use the, find another formula for another loop. And I'll go ahead and do this one here, this little tiny one. And then I'm going to add them together. So 9. So go around, go around, go around. Now that's 4I1. And then again, that is another 2I, right? When we come back around this little tiny loop. So instead of just putting in 2I, I went ahead and substituted that in. So let's simplify that a little bit. 4I1 minus 2I1 minus 2I2, which is 9 minus 6I1 minus 2I2. Alright, so I have two formulas here with two unknowns. 4 minus 5I2. I'm just rewriting them one below the other. So what I'm going to do is I'm going to do systems of equations, essentially, and I'm going to simplify it so that I can come up with an expression for one of these guys. So what I'm going to do is I'm going to multiply this first one by negative 3. So it becomes negative 12 plus 15I2 plus 6I1. And then I'm going to add that to this guy. So my I1s will cancel out. I'll get negative 3 plus 13 I2. And remember that all of that has to equal 0. So that means 13I2 equals 3, and I2 equals 3 divided by 13, which is 0.23. Alright, so now we have an expression for I2. We can come back up in here to either one of these formulas. Let's just use the first one. Minus 2I1, and that has to equal 0. So 5 times 0.23. 4 minus that is 2.85. Minus 2I1 So that means that I1 is 1.425 amps. So here's I1, here's I2. Now all we have to do is come back up here to our original formula to find I. I is 1.425, I1 is, plus 0.23. That makes our total current be 1.655 amps. Alright, so that's how you use Kirchoff's law, or rules, to solve a circuit that might be a little bit more complex than what you guys are used to solving. We have loop rule, which is essentially our conservation of energy, and then we have junction rule, which is our conservation of charge. So they can be put together. This is just an example of just using loop rule. This down here is an example of using loop rule and junction rule to solve a circuit. Alright guys, I will see you all after the weekend.